Good morning. So, I am going to present a lecture for BSc 5th semester, subject Mathematics, Paper 1, Real Analysis, Chapter Riemann Integration, Program BSc, and name of the presenter, that is myself, Dr. Sridhar. So in this session, we are going to learn about the upper and lower integrals, then Riemann integrals. Okay, so let us start. So Riemann integrals. To define Riemann integrals, first we should know what are upper Riemann integrals and lower Riemann integral. So here upper Riemann integral means the infimum of the set of upper sums UPF is called the upper integral of f over the interval AB. So and is denoted by the integral from a to b bar f of x dx. That means what? The infimum means what? The infimum means it is the greatest lower bound. The infimum means it is the greatest lower bound. So it is the upper Riemann integral means it is the greatest lower bound of all the upper sums is known as upper Riemann integral, and it is denoted by integral from a to b bar f of x dx. So therefore, thus the upper Riemann integral from a to b bar f of x dx is equal to infimum of upper sum UPF, where P is a partition of AB. Okay. Similarly, we define lower Riemann integral. So here lower Riemann integral means it is the supremum of set of lower sums LPF, okay, called the lower Riemann integral over the interval AB, and it is denoted by integration from a bar to b f of x dx. So here the supremum means what? The supremum means the least upper bound. The least upper bound. So the lower Riemann integral is the least upper bound of the set of lower sums. Lower sums. Okay, so it is called as lower Riemann integral. So therefore here the lower Riemann integral from a bar to b f of x dx is equal to supremum of all lower sums, that is LPF, where p is a partition of AB. Okay, so this is about upper Riemann integral and lower Riemann integral. So now we see what is a Riemann integrable. Now a bounded function f is said to be Riemann integrable over the interval AB if its upper and lower integrals are equal. If its upper and lower integrals are equal, then we say that the function f is a Riemann integrable. Okay, so and it is denoted by integration from a to b f of x dx. Okay, and the value is called as, so means when upper and lower sums are equal, okay, then the value it is called as the Riemann integral. The value is called as the Riemann integral. So next we have some theorems. The first theorem we have, that is the lower Riemann integral cannot exceed the upper Riemann integral. So that is integration from a bar to b f of x dx is always less than or equal to integration from a to b bar f of x dx. So here integration from a bar to b represents the lower Riemann integral. Integration from a to b bar represents the upper Riemann integral. Okay, so now proof. What we do? First we consider P of AB be the partition of the interval AB. Let P of AB denote the set of all partitions. Okay, let P of AB denote the set of all partitions of AB. Okay, so then since we know that no lower sum can exceed any upper sum, no lower sum can exceed any upper sum, always the lower sum is less than or equal to upper sum. So therefore what we have, if you consider any P1, partition P1, then lower sum of P1F is always less than or equal to upper sum of P2F, where P2 is a partition of another partition of AB. Okay, so L of P1F is always less than or equal to U of P2F. Call this equation as 1. Then let P1 and P2 belongs to P of AB. P1 and P2 means what? These are the partitions, different partitions which belongs to the set of partitions, that is P of AB. Next, keeping P2 fixed, then we observe that the set of lower sums of the partitions P1 then has an upper bound U of P2F. Because here from this equation 1, L of P1F is less than or equal to U of P2F. So from this we conclude that as a set of all lower sums, L of P1F, where P1 belongs to the interval AB, has an upper bound U of P2F. Okay. Then again we know that integration from a bar to b f of x dx already we defined, that is the lower Riemann integral is nothing but what? Supremum of all lower sums. So this by definition. So by definition we have integral from a bar to b f of x dx is equal to supremum of all lower sums where P1 belongs to AB. Okay, so now but supremum means it is the least upper bound. Supremum means it is the least upper bound, means it is the least of all upper bounds. So therefore supremum is always less than or equal to any upper bound. So hence we get integration from a bar to b f of x dx. So integration from a bar to b f of x dx is less than or equal to U of P2F. So why this comes? Because here supremum means what? Integrate from this equation, supremum means integral from a bar to b f of x dx. Now this supremum is less than any upper bound. So therefore the integral from a bar to b f of x dx is less than or equal to upper bound means U of P2F for all P2 belongs to partition of AB. Now call this equation 2. Now again from this equation 2 it follows that the set U of P2F, the set containing upper sums of P2F where P2 belongs to partition of AB, has a lower bound, because now see here this is less than or equal to this U P2F means what? This has a lower bound. So and that lower bound is nothing but a bar to integration from a bar to b f of x dx. So therefore has a lower bound a bar to b integration from a bar to b f of x dx. And we also know that the integration from a to b bar f of x dx, that is upper Riemann integral, right? By the definition of the upper Riemann integral, integration from a to b bar f of x dx is equal to infimum of all upper sums, okay, where P2 belongs to AB. Now again what we can do, so here any lower bound cannot is always less than or equal to infimum. Infimum means what? Infimum means it is the greatest lower bound. It is the greatest lower bound. So any lower bound is always less than or equal to greatest lower bound. So hence we get integration from a bar to b f of x dx. So now this is a lower bound. This is a lower bound is less than or equal to infimum. So infimum means from this equation, infimum means it is equal to a to b bar integration from a to b bar f of x dx. So therefore here I replace this lower bound by integral from a bar to b f of x dx less than or equal to infimum means from this equation, infimum means integral from a to b bar. So therefore I replace here infimum integral from a to b bar f of x dx. So this is the theorem proved. Okay, so next we have another theorem, that is Darboux theorem. Darboux theorem, it states that let f be a bounded function defined on the interval AB, then to every epsilon less than or equal to 0 there corresponds delta greater than 0, such that the first one, upper sum is always less than or equal to integral from a to b bar f of x dx plus epsilon, and second one, lower sum is always greater than integral from a bar to b f of x dx minus epsilon. This is for all partitions P such that norm of P is less than or equal to delta and the norm of P being what? It is the norm of the partition P. Norm means it is the greatest length of all the intervals. So this is Darboux theorem. Next we solve problems. Now the first problem is, show that a constant function is integrable. Show that a constant function is integrable. Okay. Now to prove this one, let f of x is equal to k for all x belongs to AB. So constant function means what? F of x is always a constant for any value of x belonging to that particular interval. So let this be a constant. So where k being constant. So now as f is bounded function, now let the partition P is equal to A equal to x0, x1, x2 dash 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 xn equal to B be any partition of AB. Partition of AB. Now if take let MR, capital MR and small mr be the supremum and infimum of f in the interval xr minus 1 to xr. So then clearly the function f of x is constant, that is k. So therefore, and it contains only one element, that is k only, and therefore its supremum is again k and infimum is also again k. So therefore capital MR is also k and small mr is also k, is also equal to k. So now therefore the upper sum P of f is equal to, by using the definition, summation from r is equal to 1 to n capital MR delta r, which is equal to summation from r is equal to 1 to n capital MR is nothing but k into delta r is nothing but length of the interval, that is xr minus 1, which is equal to k into summation from r is equal to 1 to n then xr minus 1. Okay, so now expand using summation from r is equal to 1 to n, then we get k into bracket x1 minus x0 plus x2 minus x1 and so on up to xn minus 1. Now in this, see here, this plus x1 then minus x1 then plus x2, next again here also one x2 will come when we take the third term. Okay, so that plus x2 and minus x2 will get cancelled. Similarly plus x3 minus x3 plus x4 minus x4 and so on, they will cancel each other. Only the two terms will left, that is one is xn and another one is x0. So therefore k into xn minus x0, which is equal to k into xn means b and x0 is nothing but a. So therefore which is equal to k into b minus a. As b is constant, a is constant, k is also constant, so total this whole term becomes a constant. So therefore we get the upper sum is a constant. Now take lower sum. So again lower sum is given by LPF is equal to summation from r is equal to 1 to n small mr delta r again which is equal to summation from r is equal to 1 to n small mr is nothing but k, again delta r is length of the interval xr minus 1. Okay, so again expanding the same way as we did in this case. Okay, and then we obtain again k into xn minus x0, which is equal to k into b minus a. Again it is constant. So what we get? Upper sum also we get k into b minus a, that is constant. Lower sum also we get k into b minus a, that is constant. So therefore both lower and upper sums are equal. So both lower and upper sums are equal. Therefore the constant function is integrable. Both lower and upper sums, Riemann integral, are equal. Therefore the constant function is said to be Riemann integrable, or simply it is integrable, right? So next is this is all about the first problem. Next we go to another problem. So now here it is given by, if f of x be defined on the interval 0 to 2 as follows. So that is f of x equal to x plus x square when x is rational, and equal to x square plus x cube when x is irrational. Then f is integrable, not integrable, upper and lower sum don't exist. Then fourth one, none. Okay, so try this problem again by applying the method as I have shown you in the last problem. So find the upper sum of this f of x, find the lower sum of f of x. If both are equal, then we say that it is integrable. If both are not equal, then it is not integrable, right? So here the answer is B. So the answer is B, that is not integrable. So you get both upper and lower sums are not equal, right? Next, every bounded function is, first one is Riemann integrable, second need not be Riemann integrable, then third one is none. Okay, so take any bounded function, bounded function. Okay, so constant function is also a bounded function. Take bounded function, find the upper and lower sums of that, then show that both are equal. If they are equal, then it is Riemann integrable. If they are not equal, means they are not Riemann integrable. Okay, so the answer is B, need not be Riemann integrable. So then try to solve this problem. Next comes necessary and sufficient condition for integrability. So a necessary and sufficient condition for the integrability of a bounded function f is that to every epsilon greater than or equal to 0, there corresponds delta greater than 0, such that for every partition P whose norm is less than or equal to delta, the oscillatory sum WPF is less than epsilon. Or in other words, we can say that the upper sum, that is UPF minus LPF, is less than epsilon. So this is the condition for necessary and sufficient condition for any function to be integrable. If you want to check any function f of x for its integrability, then it should satisfy this condition. If it satisfies this condition, then we say that the given function f is integrable. Okay, so that's all for today's session, and we'll continue in the next day. Thank you.